Maybe the most surprising things about the order of the snow crystal are the details of their branches, the variability in their branch widths, and the regularity of their side branches. In the early 2000s, I first started to wonder, what processes control these structures? Now, for the other type of dendrite, such things had been analyzed in thousands and thousands of research papers going back decades. But for the ordered type of dendrite like snow, I found essentially nothing. So I started to think about it in terms of layer nucleation, and this is how I think the side branching works. First, let's run through this without the explanation. Focus on one half of the branch tip. The other half is its mirror image. Now this vertex track here is the spinal ridge that I mentioned. It tracks the history of this vertex, and this one does the same for the side vertex. Okay, the layers for this phase are fed by nucleation at A. They come racing down here. And the side here is fed by layers that nucleate less rapidly from C here. At a later time, this face has grown to here, and this face to here. Instead of continuing along constant conditions, let's say the conditions change and now the growth rate is significantly faster. So now the layers are nucleating faster, and they start bunching up and clustering, say, right here. So a narrower tip starts to emerge. So now the layers that once spread across this entire face, they now stop here. And now what feeds new layers on this? Well, this region's a little shadowed by vapor, and so they're fed by layers that are nucleating at C and coming up this way. At the same time, the increase in the growth rate has caused clumping along the side here, C. Now, if the change in conditions was large enough, clumping will also occur with the layers coming from this vertex. So this gets clumped together and starts to separate. A side branch is formed. Now, this side branch is led by these two faces, which grow at the same rate because they're both being fed by layers nucleated from the same point. So if you look at the angles here, you'll see that this is going out at 60 degrees. Now the same thing is happening over on this other side here. So your branch tip then sprouts two side branches on each side at 60 degrees. The important thing is that layer nucleation requires a certain growth rate increase for this to happen. And here we have a recently published illustration of this process. Start down here at the bottom. Here you have a relatively wide tip. Then later time, something's happened and the growth rate has changed. This tip is starting to spurt forward and it's getting narrower. And these, see later time, these side branches have started to form. And they're growing, and now you can definitely see that they're separating from the tip. A brief review here. The branch tip grows straight because its two leading faces are being fed by layers nucleated from the same or essentially the same point. Thus they grow at the same rate. The vapor surrounding this is mirror symmetric, so the tip remains so, or nearly so. And roughly the same applies to the side branch, except it grows into a likely asymmetric vapor density region. So a side branch might have one side that's a little thicker than the other, but it grows straight and it grows at 60 degrees to the tip. So I was looking at our conference logo and something just jumped out at me. Now, it's a great crystal, by the way, 6 corners and mirror symmetry along each branch. But about those side branch angles, you know, 60-degree angle is really easy to note because it's parallel to the neighboring branch. Anyway, so I tend to notice these things, and once I saw a 8-branched crystal on a person's sweater, and so I brought it up, and the person said, well, I hear that every crystal is different. Well, true, but I say, that doesn't mean anything goes. And about the crystals being all different, well, they probably have more variety than most people realize. This is the Mogono-Lee classification system. It has 80 categories, and the dendrites have just a few of these. But there's nearly endless variety within each of the categories. Now, crystal variety comes from a variety of conditions. But how? Well, one thing to note is that a crystal grown under changing conditions will not look the same as one that's grown under the same average conditions. So consider this natural dendrite. We know from Nakaya's habit map that this guy grew around -15 and near water saturation. But in a natural cloud, it had fluctuations in temperature and supersaturation. Compare it to a guy that was grown under the same average conditions, but constant conditions, no fluctuations. You can see, for example, that this one doesn't have the side branches. I would guess then that for the same size, this fellow would fall faster. And larger temperature changes can have larger effects. Here we have a capped column. First grew as a column, then changed into a regime that had faster prism face growth, about 6 to 7 degrees change, grew the caps. And this one we discussed before, it did the same thing, but then it changed temperature again by about the same amount and went back to the columnar regime. But even small temperature changes can have a lasting effect. Consider this example here on the left. It's a crystal growing at -14. It's growing at a uniform temperature, so its branch width is uniform. Then it falls into a region of air just half a degree warmer. The branch slows down, so it gets a little wider. And then it falls back into its original temperature, -14. The branch speeds up, gets a little narrower, but it leaves behind this little wider section, a little knuckle there. It's a permanent feature that's added to the crystal from just a small temperature change. A cloud has puffs of air of different temperature and supersaturation, especially clouds with large updrafts like cumulus. But even stratus clouds have a lot of heterogeneity. This shows 1,000 temperature measurements along an 8-meter horizontal stretch of stratus. Now these changes may seem small, but they add up. When I analyze data like this, I conclude that the crystal could respond to such changes, and the reason it can respond is undoubtedly due to our old friend layer nucleation, and here's how. Growth rate is extremely sensitive to temperature changes. Here's the growth rate of the prism face of a crystal grown at liquid water saturation. It's colder down here. At -10, the growth rate is just 0.1 micron per second. But as we decrease the temperature just 5 degrees, this growth rate increases by a factor of 10, reaching a peak near -15. Further cooling by 5 degrees brings it back down by the same factor of 10. Why? Well, as we cool down to -15, the supersaturation over ice, liquid water saturation, increases. Okay, look at this layer nucleation curve over here. So even though S crit for the prism face is roughly constant, at least in that temperature range, we are increasing the supersaturation. So we're riding up this very steep part of this layer nucleation curve. And at -15, we're probably pretty close to this maximum. Why does it decrease again after that? Well, that's a mystery. We don't have critical supersaturation data down there, so there's still a few possibilities. Speaking of mysteries, well, there's little mysteries and big mysteries. And what may seem like a little one may have big consequences. It's the nature of mystery. Before I only showed you part of Nakaya's habit diagram, or habit map as I prefer. The reason is that a lot of it is either disputed or simply unexplored. Even at the warm temperatures, if we go to low supersaturation, there's still a lot of dispute. And for those high clouds, those high ice clouds, the habits down there are also heavily disputed. You could say the habit map still holds quite a bit of mystery. Or if it were an old sailing map, we might sprinkle in a few sea monsters. Many other habit issues are also largely unexplored. Here are some images of crystals I grew with the device shown earlier. Related to that mystery about the low supersaturation growth, when do defects control growth? These images show some evidence for it. At very low supersaturations, the crystal faces grow at different rates. Some of them grow so much faster that they vanish. Hollows are common on columns in the atmosphere, especially in the high clouds. But when exactly do the hollows first form, and what controls their size? Down here, when droplets freeze fast enough or large enough, they may become polycrystalline bullet rosettes, like these. The initial nucleation seems to affect habit in other ways, but this hasn't been mapped out very well. And how does that microscale variability in clouds affect the habit? And what about pollutants and proximity to other crystals and droplets? And fundamentally, what is causing this strange behavior of Veskrit? All mysteries that require new experiments. And I'm really excited about version 2 of our experiments. Working with Brian Swanson of the Laux Foundation, we came up with this larger and fancier version. It should be able to go to much lower temperatures, have a lot greater control of temperature and supersaturation, and we'll be able to study initial nucleation, proximity, and many other things. So I'll look forward to banishing some of those sea monsters and reporting on things in the future. Finally, our last question. I often hear this question about water carrying a message. It came from this popular book in 2006 that said that water responded to our appreciation by turning into a nice-looking crystal. Now, the quick responding scientist or engineer would say, well, this is wacky. But hold on, the idea of a snow crystal carrying a message is neither new nor altogether wrong. Some time ago, the amateur scientist, keen observer, and photographer Wilson Bentley observed that a snow crystal was essentially a dainty hieroglyphic carrying a record of its life history. Nakia later read these messages using his habit map. The main message of my talk here is this. Because growth occurs by layer nucleation, snow crystal habit is both reproducible and ultra-sensitive to the conditions, which allows us to decipher its life history. This is about the mysterious crystalline order that comes from vapor deposition. Vapor deposited crystals in the air affect us many ways, and knowledge from the new experiments may allow us to decipher further order, improve cloud modeling, and maybe solve a microscale mystery or two. That's the end for now, and thank you for listening.